All right, so we've seen a little bit about exponential functions graphically. We've seen a little bit about exponential functions numerically, and I hope this is building some intuition for you. But I want to explore another aspect of exponential functions that involves percent. A percent increase and a percent decrease is going to involve a multiplication. And when we have a constant increase or a constant decrease, we'll have this constant multiplier, which is going to lead us to an exponential function. So let's use this word problem to kind of illustrate what's happening with an exponential model and how we could create it. And I want you to learn about the tie-in between percents and exponentials. So we got 40 stores to start, and this company plans to grow by increasing 50% of those stores each year. And we want a function that'll model this. So let's get some variables. So we'll assign t to be the number of years after the start, and n of t, the function, to be the number of stores. And let's mathematically model the first output after the start. So the n would equal 40 stores from the beginning, plus we're going to do a 50% increase. Now, what does that mean, increase? It means a percent of the number of stores. The number of stores now, which is 40. So I'm going to do 40 plus 0.50 times 40. Well, that just equals 20. And we're going to get 60 stores. So mathematically, we can see how that first point came about. And one thing we do see is there's a multiplication involved in it. Right here is a multiply. But is it a constant multiplier? Well, the problem I'm seeing is that I want a function of t, and this is not time. So I don't have really like an input-output equation here. So this mathematically will get it, but I have to get all these data points one by one by one by one, and it's going to be really hard to model this as a function. I need a multiplier that involves t. It involves the years, not the stores. Okay, so what I'm going to do is scratch this, rewind, go back to the drawing board. Now, bear with me as I analyze the graph, and I want to develop this idea percent, and remember, we're looking for a constant multiplier. At the beginning, we started with 40. Now, we kept the 40, and then we added 20 stores, which was a 50% increase. And then we started with 40 stores. Now these 40 stores happen to be 100% of the beginning. So we had 40 stores in the beginning, and in the first year we kept them all. Well, keeping all 40 stores is like saying I kept 100% of last year's stores, and we added 50%. Okay, now let's keep this going. Let's look at the second year. At the second year, now we have 60 stores. Well, these 60 stores are all 100% of the year before. So I have 100% of the stores from year one. So now in year two, I still have 100% of all 60 stores from the previous year. But we're going to add something. We're going to have a 50% increase. Now, a 50% increase, 50% of these 60 is 30 new stores. So 60 and 30, that's how we're getting the 90. Okay, let's go to the third year. So in the third year, we are keeping all these stores. So in the second year, we had 90. In the third year, we still have these 90 stores. So that's 100% of the 90 stores from last year. But we're also going to have an increase. And we're going to have a 50% increase. A 50% increase of these 90 stores is 45 new stores. So the 90 and 45, that's where we're getting the 35. Okay, so hopefully you're starting to see the idea that we got. Last one. In the fourth year, we're keeping 100% of the previous year. So we had 135 stores last year, and we're keeping all 100% of them. But we're also going to grow. And we're going to grow by increasing 50% of those 135 stores, which turns out to be 67.5 new stores. Okay, now, what's happening? So what I'd like you to notice, obviously, from each growth, there is 100 plus 50. So in effect, we could say that the growth is 150%. So if I want this value here, what if we said that we were taking 150% times 40? Well, 150, 1.5, 100, so, 150%. 100% plus 50% is the same as the decimal number 1 plus the decimal number 0.5. And so I'm getting 1.5 as a multiplier here. And 1.5 times 40 is 60. What happened on the second one? Well, it was 1.5 times 60. And 1.5 times 60 is 90. Now, here's the trick. Where did the 60 come from? 60 came from here, which came from this problem. So I'm going to substitute this back into the 60. So I'm going to take the 60 out and replace it with this. 1.5 times 40. And you can check it in your calculator. 1.5 times 1.5 times 40 makes 90. Now let's go to the third year. We had 150%. 150% of 90 is 1.5 times 90. And you can check it in your calculator. 1.5 times 90 is 135 because there is the 150%. So we're having this increase of 150% each time. And that means we wind up multiplying. But my question is, can we simplify this a little bit? Well, maybe it's not seeming simpler to you what I'm doing, but be patient. 150, 1.5 times 90, I'm looking for this constant multiplier, but where did the 90 come from? The 90 came from here, which is this formula. So I'm going to plug that in for the 90. So I'm going to take the 90 out and plug in this previous calculation. 1.5 times 90. Now, what's happening? I'm hoping you're starting to see a pattern. This one was 1.5. I multiplied it once. Here, I multiplied 1.5 twice. Here, I multiplied 1.5 3 times. Well, oops, I made a mistake. This is 40. I'm substituting in this formula right here. Okay, so we could say this is like 40 times 1.5 to the third power. We could say this one is like 40 times 1.5 to the second power. And we could say this one is like 40 times 1.5 to the first power. And now I'm seeing time. First year, second year, third year, there's a variable here. And the variable involves a multiplication of 1.5. So this is the makings of our function. We could say n of t equals 40 times 1.5 to the t power. And I encourage you to put this in your calculator, play around with it, and fill out the values and double check. So here we go. This function, if you check it with me like I did, you can see that numerically the function is modeling the situation with the stars. So we did it. We created a mathematical model that happens to be an exponential equation. Now, I'm going to sneak in some things here about exponential functions. In general, we'll study this in a minute. There is the a. That's like the stretch number that we know from our polynomials and our quadratics, times a b, that's the base, with a power. And in our problem here, a was 40 and b was 1.5. But what I want to sneak in with you is b. Where does b come from? And you might remember that it came from here. 100% plus 50%. Now, if we write 100% as a decimal number, that's number 1. If we write the 50% as a decimal, it is 0.5. Now, what is this 0.5? This is called the growth rate. So the growth rate is that 50%. Let's call that, which we're going to identify as R, versus the growth factor. The factor is the multiplier, which in this problem is 1.5. So where did the b come from? The b equals 1 plus R. where R is the growth rate. That's the 50%. We added that to the 100%, which is the 1. So this little formula here is going to be an important formula for us when we're relating exponential functions with percent increases or percent decreases. Okay, I know I packed a lot in here. We've got a lot of concepts laid out now. So what I'm going to do is start weaving all this together and looking at some examples.